Hi Zach, welcome to lesson 117. This starts on page 493 of your book. Can you believe that? 493? I'm so sad that these lessons are almost over. We are going to go over direct and inverse variation. I know you're going to say, but we already did that. That sounds familiar. But squared this time. So we're going to square the amount of fun that we are having with this lesson, okay? All right, here we go. Let's start with this. If 666 really is the most evil number in the world, then 25.8069 is the root of all evil. Get it? If it's the root of the root. Okay, all right, enough of that. Let's jump into this. All right, so this lesson talks about direct. Remember when something is directly related, it looks something like this. You have something that is directly proportional to something else, all right? And remember, when it's indirectly related, you have something that is inversely related to something else. So this is inversely related to time or whatever. And I wrote proportional to, that's my abbreviation for proportional to, and then I just wrote a ratio, like it's either directly related or it's indirectly related. But if you change that proportion sign to an equal sign, then it's going to be something like this. Directly related is some constant times the other thing that you're looking at, and indirectly related is some constant over the thing that you're looking at. So that's just a quick and dirty reminder of what we did before. So remember, direct and inverse variation statements are not always simple statements, just like I did here. A simple statement of direct variation or inverse variation. Sometimes one variable is going to vary as the other variable squared or the other variable cubed. So it could be S is proportional to T squared, or S is inversely proportional to T cubed. So it's things like that. We're just taking it to the next level. So let's look at some statements right here, and then the equation that they imply, because you are going to have to figure out what that equation is, okay? So let's look at this statement first. This is the first example between here and here, okay? The weight of a body varies inversely. Okay, let me highlight this. The weight of a body varies inversely with the square of the distance to the center of the earth. So I'm going to put the weight of a body. Now when it says varies inversely, that's when I'm going to put the equal sign. And I know that there's going to be a fraction on the other side because it says varies inversely. What does it vary inversely with? The square of the distance. So on the bottom, I'm going to put distance squared. Okay, let me read it again. The weight of a body varies inversely with the square of the distance to the center of the earth. Okay, that's all they tell us. Now, you notice when I did proportions, I was doing 1 over. But in these examples, it's going to be some constant. Instead of 1, it's going to be some constant, and we're going to write that there. So this is the equation that first one implies, okay? So I'm going to take this now. Whoops. I just want to, oh, poop. Okay. All right. I guess that's not going to work for me. So I'm just going to, I wanted to make this a little bit smaller, but maybe I'll just erase it and we'll do the next problem. Okay. So we did that one. The next problem is this. The distance required to stop is directly proportional to, so I'm reading those words directly proportional. So I'm going to say distance required to stop is directly proportional to, so I'm going to put an equal sign, and then I'm not going to put any sort of fraction because it's directly proportional to the square of the velocity. So that means as velocity goes up, the distance goes up. That makes sense. Okay. The distance required to stop is directly proportional to the square of the velocity. Now, the only thing I have left to put in is the constant. So I'm just going to put that here. So the distance is directly proportional to the square of the velocity. Okay, perfect. That's the whole equation. All right. All of these are going to have a constant. Usually when I sometimes I just think of the number 1 as the constant, and that's why I tend to leave it out. But I want you to put it in because you'll definitely need it for these problems. Okay, let's do this one. The price of a diamond varies directly as the square of its weight. So I'm going to put the price of the diamond varies directly, so there's going to be no fraction on the other side because it varies directly, as the square of its weight. So it's going to be weight squared, and I'm not going to forget about the constant. Usually they put the constant in first. It doesn't have to be that way, but you know. All right, so that's it. You're starting to get it, right? So as the weight of a diamond goes up, the price is going to go up. Not just going to go up, but it's going to go up with the square of the weight. So it's going to go up quite a bit as you change the weight. All right, let's do the next one. We did that one. Let me get a nice bright color. Okay, the strength of the field, so I'm going to put S for strength, is inversely proportional to, so I'm going to put a fraction sign on the other side, is inversely proportional to the cube of the radius. So radius cubed goes on the bottom. I would put a 1 on the top, but it's not just going to be a 1, it's going to be the constant. And then I'm going to read it again just to make sure I did it right. The strength of the field, so S, is inversely proportional, got it, to the cube of the radius. Yes, so this means that if the radius goes up, the strength of the field is going to go down. Not just going to go down, but go down by a lot because it goes down by the cube factor of that radius. So that's going to be a big change. All right, so these problems are solved in the same way that we solved simple variation problems before. Okay, so the first thing that we do, we are going to recognize that it's a variation problem. Then you're going to write down the equation. I know I put an R for that for the mnemonic, but just go with it, okay? Write down the equation. Find the constant. Insert the constant into your equation that you wrote down here. So plug it in. That means stick it in, plug it in. Solve for the required unknown. And my mnemonic for that is Verks. That's why I put like a Russian guy here. This is Vladimir Putin. He might say, do what works. Here. So here we go. Do what works. This is my mnemonic. Ha ha ha. I'm so brilliant at these mnemonics. Do what works. And what works means is, and you have to say it with a Russian accent like that. Okay, first you recognize that it's a variation problem. Then write the equation. Just go with it. Then find the constant. Then you're going to stick it in and solve. Stick it in and solve for the unknown that you are trying to figure it out. Okay, a lot of talking. Let's do an example. Yeah, you're going to love these examples. It's going to be great. Okay, example 117.1. The distance required for an automobile to stop is directly proportional. So these are your key words that you're dealing with a variation problem. It's directly proportional to the square of its velocity. If a car can stop in 200 meters when it's going 20 kilometers an hour, what's going to be the required stopping distance when it's going 28 kilometers an hour? Okay, so first of all, V. You are going to do what works. What does the V mean? It means figure out that this is a variation problem. Is this a variation problem? Yes, it is. So check mark. We did that. Then we're going to go on to R. We're going to write our equation down. Now, I have to read it a couple times to make sure I write the correct equation. Let me get a nice bright color. So, the distance required for a car to stop is directly proportional, so there's going to be no fraction, to the square of its velocity. And then there's going to be a constant. And then read it again while you look at your equation to make sure you got it right. The distance required for a car to stop is directly proportional to the square of its velocity. Directly proportional to the square of its velocity. Perfect. Now, do what works. We are going to find K. So we solve for K. And they gave us enough information to solve for k, because if they said a car can stop 200 meters when it's going 20 kilometers per hour. So let's plug in what we know. If it can stop in 200 meters, so that's going to be 200 instead of, oh no, did my thing freeze? Oh, I bet my Apple Pencil lost battery. Yep, look at that battery percent. It's 0%. Okay, I'm just going to tell you what we're going to do here. Instead of D, you're going to write the number 200. You're just going to keep the K. And then you're going to plug in for velocity 20, because it's 20 kilometers per hour. And then you're going to solve for K. And if you look on your book on page 493, this is what they did. And for K, they got the number 0.5. Do wat werks. Now that you know K, you have to do S and S. Stick K in to your original equation, and then solve for the unknown that you want. Stick it in and solve it. Do wat werks. So what do we stick in? We stick in the K that we just figured out, because K is a constant. It's always going to be the same thing. So now that you figured out that K is 0.5, you plug that into your equation. So you're going to have D, oh, I can't write anything, can I? Let's see if I can do this. No, let's see. You're going to have, let me get a different color. That's not bright enough. D is equal to 0.5 v squared. Okay, now we stuck in K. Now we solve for the unknown that they want. They want the new stopping distance. So what is the new stopping distance if your velocity is 28 kilometers per hour? And you have to square that, remember. Do the math, and you will figure out that D is equal to 392 meters. Don't forget your units. And also remember that it's very important that you keep your units consistent. So if they give you kilometers per hour and they want to know what the new speed is, the answer is going to be in kilometers per hour if you kept your units consistent, okay? Let's do example 117.2. This one's about a falling body. That's why you get to look at this little GIF here. I don't know. It's about a falling body. So that's what I got for you. Okay. All right, let's go into it. It says, the distance a body falls, and I don't think they really mean a body. I think they mean like a bowling ball or whatever, anything that you can make fall. The distance a body falls varies directly. Aha, some key words right here. So I'm going to do wat werks. I know that this is a variation problem. So I'm going to go check on that. Yep, we did that. It varies directly as the square of the time that it falls. Now, is this equality going to have a fraction in it? No, because it varies directly. Okay, so let's write the equation as far as we know it. So the distance a body falls varies directly as the square of the time that it falls. And then I'm going to put in my constant right there. Okay, so that's R. I'm doing wat werks. Now I'm going to solve for K. Solve for K is the next part of the problem. So they give you an example to help you to solve for K. And the example is, if it falls 144 feet in 3 seconds. Okay, so we're going to plug those in and then solve for K. So let's plug in. Distance is going to be 144 feet is equal to K times T, which is 3 seconds squared. So then this is going to be 144 is equal to 9 times K, all right? Instead of this, it's going to be 9 times K. Then we divide both sides by 9. K is equal to 144 over 9, and that's the same as 16. Okay, easy peasy. So K is 16. Now that we know that K is 16, we've got half the battle won. right? Because k is a constant. It's always going to be 16 in this problem. So now we stick it into our original equation. Stick it in. That's the next S. Do wat werks. So let's stick it in. D is equal to 16 times t squared. That's our new equation. Now solve for the thing that they want us to solve. They're saying, in the original problem, how far will it fall in 10 seconds? Okay, easy peasy. They give us a 10, that goes right here, squared, times 16, and you're solving for D. Easy peasy. Do the math on that. You're going to see that you will get 1,600 feet. Sweet. Let's do the next example, 117.3. This one is about body weight. I think I've lost weight. Oh. Is that the one where Homer gets in shape? I can't remember. All right, let's do 117.3. And this says, the weight of a body on the surface of the earth, it says on or above the surface of the earth, varies inversely. Aha, I know those key words. That means that this is a variation problem. So check mark on that. We are going to do wat werks. So let's highlight or let's underline the key words as we go. So it varies inversely. That's important, especially that inversely part, because I know that there's going to be a fraction involved. It varies inversely, so we've got weight, varies inversely with the square of the distance. So I can go ahead and write my equation just with that information. The weight of a body varies inversely with the square of the distance. And on the top, I'm going to write a K. Sweet. I'm just going to erase this just to make it not confusing. Okay, so I did number 2. I wrote the equation. And the distance is the square of the distance from the body to the center of the earth. Okay, now, if a body weighs 10,000 pounds at a distance of 500 miles, so they are giving you some information there to solve for K. So if it weighs 10,000 pounds and the distance is 5,000 miles from the center of the earth, so I'm going to start plugging those things in. It's going to weigh 1,000 pounds equals K over distance squared is 5,000 miles, that whole thing squared. Okay, so then we can divide both sides by 5,000 miles squared. Erase this. K is equal to 1,000 divided by 5,000 squared. So that is going to equal, that's a big, huge number, isn't it? Oh, did I do it wrong? Oh, yeah, because those things are multiplied by each other. I think I did it wrong, Zach. Sorry. Yeah. To solve for K, here, I'll just solve for K in this original equation. So it's going to be K is equal to weight times D squared. So to solve for K, it's going to be weight, which is 10,000, that's a comma, times D squared, which is 5,000 squared. That is still a humongo number. And they simplified it in the book to 25 times 10 to the 10. You might need to use your graphing calculator on that. Okay, so now it says, how much would it weigh? So, okay, if we're doing what works, we solved for K. We know what K is. K is this ginormous number. Then we solve for we stick it in our equation. So the W is going to be equal to this humongous number divided by D squared. Okay, now I can erase this to make it less confusing. Okay, and then stick in the other parts of the equation and solve for the unknown. So how much would it weigh? So they want to know W if it's 50,000 miles from the center of the earth. So how much would it weigh? They want us to solve for that. If it's 50,000, and don't forget to square it. You're definitely going to need a calculator on this one, but you could change 50,000, this is what they did, to 25 times 10 to the 8th. I don't know if that makes it easier or not, but it turns out to be 100 pounds. Whew. All right, you do that one and see if it makes sense to you, because that one was a little bit confusing for me. All right, have fun with your homework today, Zach. Love ya. Bye.